Welcome. So we basically finished this problem in class, and you either saw it live or you watched the video that was also posted with this. And I just rewrote it a little nicer, added a little columns, added some numbers so you can follow along. And so step one, we did our diagram and we used the information that was in the question. The fact that we're given surface area, that our prism has a square base, it's a box, and that it is open on one side. We use that to get our diagram and to get our equations. We were maximizing volume here. Formula for volume is the area of the base times the height. But we can't have two variables. So we use our secondary equations to take the information that we're given, the constraints, and reduce the primary equation to one variable. Right? And so we can take surface area of an open box, which would just be the bottom of the box plus the four sides, right? And all the four sides are the exact same dimension since this is a square. I'll add a little h in here. Right? So you've got one base, which is x times x, or x squared, and you've got four sides, which are x times h. Right? And so then we could solve for h, isolate h, and then we'll substitute for h back in the primary equation. So that's why we have primary equation at two steps, 2 and 4. 2, we wrote the equation, and 4, we made the substitution, and then 5, we could simplify, and then, because it'd be nicer to use a power rule if we just simplify it, and then take the derivative, and then we set the derivative equal to 0 and solve. That gives us the critical points, right? So the whole reason we set that equal to 0 is to find the critical points. Right? And so when we solved, we got 2. Right? Once I reduced, we could factor that, and it'd be x minus 6 and x plus 6. Actually, it'd be 6 minus x and 6 plus x, but it'd be the same thing. Of course, you can't have a negative dimension, so you can throw that answer out. That's where your feasible domain comes in. Right? So I'll put it over here. The feasible domain, you know that x is at least got to be greater than 0, right? Can't even be equal to 0. Otherwise, you don't have a box. Right? You don't really have to figure out what the largest could be, but you do know you're expecting positive numbers, and you can throw out anything that's negative. All right, so then we can use our second derivative. You'll look at step 8 there. I think this is where we kind of ended in class, so this is just picking up at the very end of this problem. So second derivative, take that and substitute your critical point. So the first derivative, dv dx, was 27 minus 3/4 x squared. Right, and hopefully you see that I'm pointing right here. And then derivative of that, d2v dx2, we just take the derivative. So derivative of 27 is 0. The derivative of the negative 3/4 x squared would be negative 3/2 x. And then you're going to substitute your critical point, because that will give you information and verify that, yes, this is a maximum. Right, this is giving us the maximum. So if you plug in 6, you get a negative number. Right? Remember to interpret that. What does that mean if I take the second derivative and I plug in a critical point and get a negative number? Right? So we interpret the second derivative. Since f double prime of 6 is less than 0, x equals 6 is a relative maximum. You've got a concave down function here. And then on the next page, I had so much space actually to just answer the very simple question. See, I wrote huge. So we needed to use the secondary equation. What happened to my word, to solve for h, so that we were first asked to find the dimensions that produce a box with maximum volume, which means we need to solve for that last dimension. And remember, on the other page, we had previously solved for h. So h was 108 minus x squared divided by 4x. You plug in the 6, h is 3. And then to find the volume, just plug it into the formula for volume. It's the area of the base times the height. The area of the base, it's a square, would be 6 squared at 36. And so your volume is 108 inches cubed. Kind of interesting. At first I thought, oh, did I make a mistake? And then I looked back at my work, and no. It just happens that the open box, the surface area of the open box, is the exact same value as the volume in this particular case. Interesting little problem. So I kind of recapped that one because we kind of ended in class right before the end of that problem. Let's go to problem number 2 in your notes. Each problem in this particular set of notes is going to get its own video, all right? So that the videos aren't too long and I'm not cutting videos, cutting a problem in half. So a box is to be built from a rectangular piece of cardboard that is 25 centimeters wide and 40 centimeters long by cutting out a square from each corner and bending up the sides. All right, so I have done this in the past with classes, and you got a piece of cardboard. And I can show you the models. And actually, I don't really need to make that big. You don't need a humongous diagram. So this time, and by the way, I'm going to try to work from left to right. So here's our diagram. All right, so I'll just make that a little bit smaller so I don't run out of space here. All right, so there's our diagram. So we have this piece of paper or piece of cardboard. It's 25 centimeters wide and it's 40 centimeters long. But you can make a box out of a piece of cardboard if you simply cut off corners. And how much you cut off will impact the volume. You might get more volume, you might get less volume. You cut off too much, you can't make a box out of it. You just have a pile of scraps, right? So how much we're going to cut off, we don't know, right? But since we don't know it, let's give it a variable. So let's call it x. Right? So what we want to cut off is x. And you do have to cut off squares. If you cut off something else, you're probably not going to make anything. You're definitely not going to make anything. It's going to be like sort of this strange oblique figure. Sides probably won't meet. All right, so we're cutting the same amount from each side, so we can just fold. Right, so you'd fold right here, right, and here. These would be your fold lines. Right, so those are your fold lines, right, and they give you their box. I'm going to get rid of this part here because actually, if I'm going to make anything solid, I should really make the cut lines. So I'll make the cut lines solid, and then I can make the box dotted. Maybe that'll be easier. There you go. So there's the cut lines, all nice and solid, and I'll make it even in a really light color so it doesn't get in our way. Yep, come on. And hopefully you'll still see it. All right, so this represents the bottom of your box there, right? And then these would be the sides of your box because you'd flap them up and so forth, right? So there we're cutting it out so we can make a box. And you want to find the corner that will produce a container that will hold the most soup. All right, so I hope this is very sturdy, waterproof cardboard. Otherwise, you'll probably have some soppy container here. But let's just trust that the soup isn't going to go through. And this isn't a can of soup. You're making a box of soup. Because, well, why not? Why not have it be a box of soup? So there's our diagram. All right, so I'm going to try and preserve space. I'm going to go, just going to keep going down the column here. All right, so the next thing we're going to do is we're going to write the primary equation. We'll list the primary and secondary equations over here, and then we'll work with them a little bit further over. All right, so I usually start with my primary equation, and then I realize, oops, I need something. Right? And actually, this is one of the few cases, though, where the primary equation and your secondary equation is going to be able to be written together. Many times you start your primary equation, oops, you don't know that variable, oh, you got to solve for that variable, or you have this constraint that you haven't taken into account, right? And then you write secondary equations using those constraints, and together they create what you're going to be solving and taking the derivative of. But sometimes you can write your primary equation and secondary equation together. And this is one of those cases. Right? We are finding volume. Right? So volume is still the area of the base times the height. But the constraints are going to be built in when we figure out the base. Right? So the base, right, was, maybe I should have wrote it a little darker, but here's our base right here, right? Our base of that box is created by cutting out those squares, right? That becomes the base of the box. All right, so notice that the base of the box would be 40 centimeters times 25 centimeters, except you cut all those corners out, right? And so you cut X amount from the bottom, you cut X amount from the top, you cut X amount from the right-hand side, you cut X amount from the left-hand side. Right? So now, if we look at our box, if we want to just represent the blue line vertically there, it would be the length of we started with 40, but you cut an X here, right? And you cut an X here. By the time I'm done, it's going to be all colored in, right? So this would be 40 minus 2X. You cut out 2 X's. Same thing on the bottom, right? You cut out an X there where we already colored it in. You cut out an X here. So this would be 25, but you cut out 2 X's. That's going to give you the bottom of your box. Let's actually draw this, what the box is going to look like three-dimensionally, and that might also help you see everything, right? So here's our little box. Right, and so the bottom is or what I chose to draw at the bottom, is the 25 minus 2X. The sides would be the 40 minus 2X. But what about the height? Right? So notice when you pull up those flaps are going to be equal to that dimension there, and that gives you your height. So your height is X. Right? So here I think the two-dimensional helps you set it up properly. The three-dimensional helps it make sense. So now we're going to just combine those measurements we listed above with our formula for volume. Right? So the area of the base, it's a rectangle, right? And so it's going to be the one dimension, 40 minus 2X, times the other dimension, which is 25 minus 2X. And then, of course, the height of the box is just X. Right? We'll want to simplify this. So let's, in this little corner here, let's simplify that. We'll FOIL. We're not going to want, you can't have 3 products here. So let's FOIL, and let's just get this to be a polynomial, and then we can use the power rule. All right, so 40 times 25 is going to be, well, 4 times 25 would be 100. So that's going to be 1,000. 1,000. And then we have negative 80x and negative 50x, right, if we multiply the outside and the inside. So that's going to be minus 130x. And then the last two terms would be positive 4x squared. And then let's just distribute the x, right? And then we can deal with taking the derivative in the next page, or the next column there. So this would be 1,000x minus 130 x squared plus 4x cubed. Guess I should have made this go out a little farther. There we go. Oops. Lost part of my box. I think I'm kind of stuck with this in the middle here. I'll erase it and rewrite it. Just make sure you can read it. Oh, all my beautiful work. All right, so that was 25 minus, 2x times x, and then this was plus 4x times x, and then 1,000x minus 130 x squared plus 4x cubed. Oops, we lost an x squared. 4x cubed. All right, so there we go. So now let's continue on. All right, so we've already taken care of the primary equation and the secondary equation. So now we want to take the derivative. That's going to be our step 2 there. All right, so step 1, actually our step 3. So step 1 was our diagram. Step 2, we did the primary and the secondary equations together. Sometimes your diagram will lend you to doing that, right? And then I want to take the derivative. So we have, I'm just going to write the equation again. V equals 1,000x minus 130x squared, and then plus 4x cubed. Some nice little power rule there, right? So dv dx, because this is the derivative of v with respect to x. All right, so by the way, you can only have one variable. The v doesn't count, right, because that's going to be 0. Right? All the time we're going to be setting that equal to 0 to find our critical points. So that one doesn't count. You're still taking the derivative of it, but it's not going to count as having a variable when you're trying to solve. You can only have an x here. We only have an x, so that's okay. Right? You can't have two variables. So derivative of 1000x is just going to be 1000. Derivative of negative 130x squared will be negative 260x. And then derivative of 4x cubed will be 12x squared. All right, step 4, you're going to set the derivative equal to 0. And we'll find our critical points. All right, so we have 0 equals 1000 minus 260 plus 12x squared. I prefer the x squared be first. I also notice they're all at least divisible by 2, not 3. 26 isn't 260 isn't divisible by 3. How about 4? Yes, 4. So let's divide everybody by 4. And I'm going to write the 12x squared, which in this case is now going to be a 3x squared. All right, so 0 equals 3x squared minus, so that would be 65. Oh, somehow we lost the x. There we go. 65x, and then 1000 divided by 4 is going to be 250. All right, so this is not an easy factor here. Divides to give me, multiplies to give me 7. Oh, yes, maybe. Well, let me think. No, probably not going to be. Oh, wait. I think it is. I take it back. So multiplies to give me 750, adds to give me 65. I got it. It's going to be 0 equals 3x squared. It's going to be negative 75. Isn't it? Negative 75x and positive 10x? Let me check, see if that works. No. Wait. No, yes, maybe so. All right, if this doesn't work, we'll use quadratic formula. All right, so 3 times 250. And then, yeah, that's going to work. That's going to work. Yay! All right, so sometimes if you just stop and think for a moment, all right, I just double checked. Yep. So that's going to be, I want to make sure I had enough zeros and everything. So 750, that would be 75 times 10, it would be negative 750, negative 75 plus 10 would be negative 65. There, you didn't have to use quadratic formula. This would be easier. All right, so first two are a group, second two are a group. Common factor for the first group would be a 3x. Right? And so that's going to be x minus 25, and then a 10. X minus 25, and then 0 equals 3x plus 10, x minus 25. Oops. And so we get two solutions here. But now let's think of our feasible domain. Right? So we have 3x plus 10 equals 0, x equals negative 10 thirds, and x equals 25. And I'm just double checking and making sure, yeah, the signs are correct. Now, 25 isn't possible, but x could be maybe 20. So if we think about our feasible domain, this is what I'm cutting out. Why is that negative? Neither one of these looks too good. Neither one looks too good. And so I'm going to pause the tape. I'm going to stop the tape right here. I'm going to double check, make sure there's no silly little errors. So I have a problem with x equals 25. And so if you think of our feasible domain, one side is 25. How can I cut out a square that's 25? All right, that would be kind of tricky to do. because that would be my entire piece of paper. So let me just double check my signs here, and we'll come right back to this problem. All right, bye for now.